evaluation of large language models. And yeah, thanks so much to Vin for reaching out and having me back on. I was previously an organizer, so see some familiar faces here of the same NLP reading group. But yeah, just like a bit about me for background is I'm a research scientist at EleutherAI. We're a nonprofit research org that has released a bunch of language models in the past, open source, including GPT-Neo, GPT-J, and Pythia. We currently do research on things like interpretability of large models, data set creation, distributed training of models, and LLM evaluation, which will be the topic. This last one will be the topic of my talk today. And we also maintain a couple of pieces of tooling for the open source ecosystem, especially for researchers. And one of these is the LLM evaluation harness, which you might be familiar with if you know the Open LLM leaderboard. It's used to power this as the backend. It was basically, there's a link here, but it was basically a library that is used for standardizing and making it easier for researchers to run across many different models and many different tasks, few-shot and zero-shot prompted evaluation. So the library was started in 2021 by some of Eleuther's original contributors, originally just to sort of reproduce the evaluations described in the GPT-3 paper, but it's since grown with the community to be sort of a one-stop shop for evaluations. Yeah. And so, yeah, so I'm going to try and go through like a bunch of material, but please, oh, is my mic not great?
Is this any better? Can people hear?
Yes.
My mic is better now?
This is a lot better.
Okay, okay. Please let me know if it stays not great quality. Yeah, so I'll talk about two recent works, but please feel free to interrupt at any point. So the first is a paper called Lessons from the Trenches on Reproducible Evaluation of Language Models. Okay, is my audio still not great, or?
It's a little bit blurry.
Is this any better?
This one is.
Something's up with my headphones. I'll just, cool, okay. Yeah, so I'll be talking about two sort of content from two different papers that we recently put out. The first I co-led and is called Lessons from the Trenches on Reproducible Evaluation of Language Models. This sort of covers a bunch of our learnings from like our time spent working on language model evaluations over the years, especially with the LLM evaluation harness. And then the second one is a recent piece of research led by Ryland Schaefer from Stanford, talking about how we can sort of build a science of predictable LLM evaluations, which I'll get into later. And so the high level sort of structure is the first part of the talk. I'll talk about some like basic details about how evaluation is performed for language models and why all the implementation details that go into these matter a lot for the outcomes of evaluation. And then talk a bit about how we can build sort of a science of LLM evaluations that are predictable. So yeah, so the first part of the talk is basically just going to be like a quick rundown of implementation details in LLM evaluation commonly. So just as like a piece of motivating info, most of the techniques that we use to evaluate language models are motivated by a huge shortcoming that we have to get around, which is basically, it's very, very difficult to evaluate sort of free-form natural language responses from a language model. So as like an illustrative example, if we ask a model, who is the current US president, we've got, can people see my cursor? Okay, maybe not, that's fine. So on the left in this green bubble, we've got basically, we ask the model, who's the current US president? And the model gives the answer of just Joe Biden, which is the correct answer that we expect. And on the right in this red bubble, we ask the model, who is the US president? And maybe it says like sort of certainly, adds a bunch of filler sentences, and then says, oh, well, the answer is definitely not Joe Biden. And then doesn't continue on from there. And so if you or I know the answer to this question ahead of time, and just sort of like eyeball it, like we could say that the one on the left is correct, the one on the right isn't. But when we do evaluation, we don't want to have to basically go through every data point in our data set and manually eyeball whether it's correct or not and sort of grade it ourselves, because we might not always give the right answer, and it would just take a while, which is not great if we want to evaluate many different models all at once. So basically, this problem of like it being hard to score language model generations for correctness is something that we could only really solve if we had like a true oracle for truthfulness, which at that point we could get a language model that scores perfectly and never hallucinates. So a very difficult problem. And so all of the common approaches for evaluation try to sort of work around this in various ways. But there's always a trade-off, and nothing is really perfect. Yeah, so the ways that people get around this are, so there's like a couple different ways that people get measurements from a language model when performing evaluation. And these are log likelihoods, perplexities, and text generation, which I'll go through in order. So log likelihoods are basically, if we have some input string X, which is say like a question or a prompt in our evaluation data set, and an output string Y, we want to figure out sort of what the probability of Y is, assuming the model has seen X. So like a concrete example of this is if we have the sentence, the cow jumped over the moon, if we feed in X and then try to figure out how likely the moon is as the next two tokens from the language model. This would be getting the probability of Y given X or the log probability of Y given X, depending on which we compute. And notably, this can be done via just sending one input into our language model, which is pretty nice. So just as a refresher, when you run an input through a language model, what you get out are these logits, which is basically for every possible token in the model's vocabulary. It's a numeric score that's assigned to that token. And so we can then take these scores per token and normalize them to get a probability distribution or a set of log probabilities for each token in the vocabulary. So if we send in the tokens x0 through xn into the, oh good, my cursor is up. So if we send the tokens x0 through xn into the model, what we get out is a probability distribution of what the model's, over the possible next tokens, of what the model's guess for xn plus 1 is. But a key fact about language models, which makes it easier to train them, for example, if you send in 2048 tokens into a language model, then you don't need to run 2048 you don't need to run 2048 steps to get everything out. You can just run a single pass through the model to do a training step. And so the reason for this is because when you pass in the tokens x0 through xn, we don't just get a probability distribution over what the model's guess for xn plus 1 is, but we also get, conditioned on tokens up to xn minus 1, what the guess of the model for xn is, what the guess for xn minus 1 conditioned on all the previous tokens, and so forth are. And we get this simultaneously when we pass in x0 through xn to the model. So basically, when we send an input x0 through xn into the model, what we get out is logits of shape, basically distribution across the vocabulary for every position in our sequence. And we can use this to figure out the model's guess for what the next token would be at every step of the input. And so using this, the way that we can calculate the log probability of Y conditioned on X is to simply take X, tokenize it, take Y, tokenize it, combine them, and then feed it through the language model. And once we get out the logits for every position within X plus Y, we can just check the relevant target. So for basically the model's prediction for what would be Y sub I in the output string Y, we just find the logit that corresponds to the correct time step and the correct true next token ID for yi, and we figure out what the probability of the model outputting that correct next token is. And we just, and then if we have the log probabilities of each of these tokens, we just sum them up to get the log probability of the string y. And so basically, we can efficiently get these conditional probabilities from a language model. And the way that this is commonly used is to perform multiple choice using log likelihoods. So if we have a question that we give to a model, like say this example question in MMLU, there are 4 answers provided that the model can choose from. And what we're going to do is we're going to have a set of 4 possible answer strings y sub I, which are the string A, the string B, the string C, and the string D. And what we're just going to do is we're going to take the prompt x and each answer string y sub I, and then calculate the log probability of outputting y sub I, conditioned on the input. And so with this, we know how likely the model is to produce each possible answer choice letter. And then we just say that the model's answer is this most likely choice A. And so this is pretty nice because it means that we can sort of efficiently calculate this. And also it means that our model has no probability of picking an answer that isn't among the 4 valid answers we have to choose from. However, there are disadvantages of this, namely that when we use language models commonly, they're used as sort of free-form interactive chatbots, engaging in conversation. And so this sort of restricted output format isn't really natural compared to how you're going to be deploying a model. And another downside is that it's impossible to evaluate, say, OpenAI's most recent models using these log probabilities because OpenAI just does not provide the full access to the logics, especially for the input prompt. So the second main way that people evaluate language models are via perplexities. This isn't super commonly used, at least in the sorts of evaluations we're going to be talking about, so I'll skim over it decently quickly. But basically, perplexity is measuring how closely you fit a given data set. And the way that you calculate this is you take the log probability of producing each token in the data set, conditioned on the previous ones per document, and you just average per all tokens in the data set. So basically, for every token, j sub I in a document, we calculate the log probability of producing that token, given the previous ones in the document are seen by the model, and we sum these log probabilities per token up over every token in the document, and then we just sum these log probabilities per document over the documents in the data set and normalize out by all of the tokens that we predicted over. And so this gets us sort of a number that measures how closely we're fitting a data set where lower is better. So this is nice to use because it's sort of easy to set up for any data set you might have, like say a couple documents from Wikipedia that you want to see how well your model models. But it's a disadvantage because it doesn't often make sense for an instruction tunes chatbot. And it's also even more distant from sort of how your model behaves realistically in a real generation scenario. And so although these sort of do have their use cases, there's another caveat here, which is that these are very finicky with respect to sort of hyperparameters that are not often documented in papers, whether they're papers sort of introducing a new language model and providing evaluations, or even papers introducing new evaluation data sets. So basically, like the tokenizer causes a lot of problems for both of these cases. In the case of perplexity, if you have 2 models with 2 different tokenizers, the total number of tokens and sort of which parts are multiple tokens and which parts are not will change the actual difficulty and nature of the task of sort of predicting each token in the data set. And so it's difficult to compare the perplexities across models with different tokenizers in this way. And there are ways to normalize for this by, say, calculating sort of the model's average log likelihood per byte of the input, or say per like white space delineated word. And this is sort of something that's not often accounted for, and sometimes tokenizers confound comparisons of perplexities. And for multiple choice tasks as well, when we are using sort of a set of answer choices where not every answer choice is the same length, models with different tokenizers will assign different numbers of tokens per answer string. And this will mean that the shorter answer strings are sort of more likely to be chosen by the model than the longer ones, which is not always desirable. And so we might want to normalize by dividing by the character or byte length of the answer string, or divide the log likelihood by the number of tokens in the answer string. But these sorts of normalizations, although they're common practice, just as common as sort of not using a normalization for multiple choice, it's not often documented which of these people use or whether they pick and choose which they use for different data sets. Yeah, Yeah, and feel free to jump in if there are questions. But so the final way, of course, to evaluate a language model is just free-form text generation. This makes sense because for much of our downstream use of language models, we're asking them to generate text for a user. And sort of like models are often trained with chain of thought as well these days, if instruction tuned, so it's sort of a realistic setting. But as mentioned before, we have this problem that we have to face head on of how do we score and calculate accuracy for these freeform generations. So one thing that we're often forced to do is just basically say, back up to a heuristic for extracting the model's answer that we can then grade against the actual true answer. So for example, if we're asking the model to sort of solve a math word problem, it might give its answer step by step, and then we ask it to give its answer in the format, the answer is number, for some number. And then we're going to basically just look for this this keyword in the model's generation and extract the number from the generation and then see if it matches our true gold standard. But we're often faced with problems where maybe if our model was just trained with a different format, it doesn't sort of produce a format we can pick up on, and so we score it as wrong, even though it's actually very performant. And there's also other tokenizer and non-tokenizer related issues that one can run into that you might not really expect or that might not be fully documented. So here's an example of two different prompts that you could imagine passing into a language model. These are both the first example in human eval, which is a common coding completion task. These two prompts are slightly different, and I'll give like 5 or 10 seconds to just look at these prompts, and if people want to put in the chat what they think the difference is or which one is better to use for a language model, feel free. Otherwise, I'll spoil the answer pretty quickly. Cool. So the prompt that's better is 1. 2 is actually a much worse prompt to use for your model. And the only difference between these two is this sort of trailing white space that's added onto the end of the second prompt, where we've got not just sort of the question being that we're asking the language model to solve, but we've also got two new lines and then a tab character as well here. And so the reason that this is a problem is because many coding models have tokens that look like, say, like a new line and a new line and then a tab character. So this like multi-white space token, or they'll have like a tab and then a return being sort of a common Python token that they use. And so if we feed the model this prompt, which already has a tab at the end, then we might prevent it from actually using its most common tokens of like tab and then return from generating a completion. And so if we actually evaluate the model with these two different prompt formats, it'll lose performance by say like 5% or something notable, depending on the model. And so basically like all these sorts of things are things that might not be easy to pick up on if you don't have access to the evaluation code, but crucially do matter. So, oh, I think there's a hand.
Yes.
Hi. Can I go ahead?
Yeah,
Hey,
please.
yeah.
Okay, so I wanted to ask about the whole prompt design from the previous slides. So I've seen people that say you should structure your prompt in such a way that looks, like say a bit more commonsensical to the model. Like, I'm not sure if you understand that, but something that a human can read with like kind of enough spaces that separates, let's say in the multi choice question now, you'll have like the question, then maybe like 2 lines, so like down, and then you put like the option phrase, and then you put like 2 lines, and then you put like the options. And people have said that that kind of helps because it's easier to read and understand, and then the model is able to separate the options from the question and then the questions from the phrase that prompts it to give an answer. So what's your thought about that structure and that opinion?
Yeah, so I guess like the main reason I shared this example is because like if a person were looking at this coding in question, like they would not really have any difference in performance, most likely, based on this like trailing white space. And so basically like the point that I'm trying to make here is that like language models are very brittle with respect to certain things for evaluation or just downstream performance in general, and that these are like not the things that you would really like expect a priori to matter a lot, but they do. Does that make sense?
Oh, okay, that makes sense. I have other questions regarding the whole harness evaluation, but maybe we can talk about that after the presentation, or when you're taking questions for that.
Yeah, sure. Maybe we can talk about the harness at the end of the presentation.
That's fine.
Okay, awesome. Thanks for the questions. Yeah, so basically, like the sort of details that I've covered here and the things that can go wrong really just account for like, am I passing the correct input that I think I am into my language model? There are many other things that can go wrong in evaluation, including like maybe how you're prompting the data set aside from this like tokenizer white space issue, or like whether you're sort of measuring on a large enough data set to get a robust measure of performance, et cetera. And so like basically, I think the point I'm trying to make here is that if you don't have public evaluation code, it's very difficult to ensure that all of these details are implemented correctly. Or if you're trying to say, reproduce someone's results precisely, it's very difficult to know that you're making all of the right tiny choices that they were. I think there's a question.
Yeah, hi. You talked about that the white spaces or the trailing slashes basically mix up the token probability. I don't know how much this actually affects the eval, because normally you don't really do much on the token probability, or you don't really shift much logic. Is this really that much of an impact?
Yeah, so in the case of like this like trailing white space issue, it actually does make a lot of a difference. Like I think it's something like 5% on an eval that you lose if you just add these like new lines at the end, just because it's sort of like out of distribution, because the model is always trained where you sort of tokenize everything in one shot. And
Yeah.
so when you tokenize the input and then the output separately and try to evaluate, like you might.
Interesting.
Mhm.
Okay, yeah, I'm done here.
Yeah, so it's sort of like these subtle like mismatches between like training and deployment are like the big reason that this is an issue. Yeah, so I guess yeah, if people have any other questions about this part of the talk, feel free to ask. Cool, yeah. If not, then I'm going to go on to talk about some of. Oh, I think someone unmuted. Yes. Okay. Yeah. So the other part of the talk is I wanted to talk about some recent work that basically like leverages these implementation details of evaluation to think about how we can build sort of more reliable benchmarks. So yeah, this work was led by Ryland Schaefer, and it's called "Why Has Predicting Downstream Capabilities of Frontier AI Models with Scale Remains Elusive?" So yeah, just as background here, scaling laws are something that's very ubiquitous in language model training and other sort of at-scale generative AI deployment and training. They can be used to take like smaller training runs and basically like answer useful questions for practitioners when you're scaling up, including say like what are the best hyperparameters that I can choose as I scale up? How should I trade off my data set size and parameter count? And more importantly, in our case here, if we scale up compute by say 10 times, what's our return on investment? How much is our pre-training loss going to go down? And so we basically just have this like functional form where based on smaller training runs of smaller models, we can predict in advance how good if we scale up our model by 10 times or maybe even 100 times if we've got a good fit and enough points, know how much our how much return on investment we'll get, how much our model will improve. But the thing is that the loss on the model's pre-training data set isn't inherently meaningful. We know that lower seems to be better, but what we really care about is how our model is going to do, how it's going to be in quality when we deploy it for the tasks that we actually care about, whether that's say like answering math questions, serving as a chatbot, performing effective tool use. And so loss is useful, but it's not really what we want. And the problem is, though, we can't easily just fit a scaling law as effectively to downstream task performance as to pre-training loss. One reason for this is the sort of commonly observed emergence abilities, which basically are curves that look like this, where up to a certain small scale, models will perform at random or at 0% on a task, and then all of a sudden they'll start doing much better very quickly. And this is termed emergence because these characteristics don't seem to be present in smaller models, but are in larger ones. And so prior work has observed that if you use a metric that isn't accuracy, that isn't just 0 to 1, you can actually smooth out these curves and sort of remove the phenomenon of emergence. But the thing about emergence that is interesting is that the accuracy metric is what we really care about. We don't care too much about whether our model is just thinking that the correct answer is slightly more likely than it was before. We care about, if you ask the model a question, is it directly going to respond with the correct answer? And so what we really want are evaluations that are not emergent like this, that are sort of smoothly predictable as we increase our investment in our models, so we can guess what sort of the final large-scale one will perform as. But we want it to still be human interpretable. We want it to still be sort of as meaningful and as useful as the direct accuracy metric. And so just as a refresher, here's sort of another visual showing how the log likelihood-based multiple choice metrics get calculated in practice. So if we start out with the model's loss that it assigns to, say, like the target string for a given benchmark sample, we just transform it by turning the perplexity into a probability to get sort of the probability among all of our tokens of outputting the correct choice. And then once we know the probability of the correct choice, what we really care about is whether the correct choice is more likely than the other incorrect choices that we have access to. So we basically ignore all the choices but our sort of 4 valid ones, and don't let the model predict anything else, zero out all of its probability and renormalize so that we get all of our choices summing to probability 1. And then we can just pick the most likely choice and get our accuracy, which if the most likely is the correct choice, then the accuracy is 1, otherwise it's 0. And so basically, if we start from the pre-training loss, or like equivalent function of the pre-training loss on a given benchmark sample, getting all the way to accuracy requires making all these changes and transformations to sort of warp pre-training loss into something that we care about downstream. And so in this paper, we're going to try and study the effect of these transformations. And so we're going to look at like this multiple choice accuracy calculation process, specifically since we sort of know all of the moving bits that are going on here. And what we're going to do is, over a couple different common multiple choice benchmarks, we're going to collect how the model scores on accuracy, or say this other metric, the probability among the vocab, or the probability among the choices of the correct choice. And we're going to collect these sorts of metrics for every sample in our multiple choice benchmark. And we're going to do this for models that have checkpoints available, either for a family of models that sort of has a number of models trained on the same data, but across varying sizes of model, or for the same model across multiple checkpoints while it was being trained. And then what we're going to do with these sorts of series of per sample metrics across scales is we'll compute the correlation between a given metric and increasing compute for each sample in our data set. And so what we end up with is a sort of distribution over potential correlation values between -1 and 1 for all of our samples in a benchmark. So this green distribution is basically an example of just about every data point in our data set being fully correlated, strongly correlated with compute. So as compute increases, so too does the metric value on this example for almost every example in the data set. This red example is basically what we would see if just about every sample in our data set were anti-correlated between metrics and compute. So it's like the metrics were steadily decreasing as we increase the size of our model or see more data. And then these others are sort of somewhere in between, whether it's approximately no correlation between score and compute for most values, or somewhere where some of them are correlated, some of them are slightly anti-correlated. And we can visualize this a bit more clearly if we turn it into a cumulative distribution function, which is basically a way of visualizing a probability distribution where the value at, say, negative 0.8 of this red curve is going to be 0.1 if 90% of our samples in our benchmark have a correlation value that is below 0.8. So our red curve gets down to 0 almost immediately because almost every sample has a very strong anti-correlation with compute. And our green curve, on the contrary, sort of stays level at 1 for a long time because almost none of our samples have a correlation that's less than, say, 0.9 or 1. Is this clear to people? I think there's a hand.
Haley, this might be a little bit off the topic question, but
Mhm.
in the multiple choice tasks, is there a possibility of also introducing permutations and then checking on the average of those permutations, basically? Because then you would have like much more robustness to the metric in itself.
Yeah, that's a good question. So yeah, so one thing is that not all of the tasks that we test have this format where you list out the possible answer choices in context. So some of them are just basically like you take not the answer letter, but you take sort of the string corresponding to the correct answer and see how likely the model is to output that string as its response. And so in tasks like those, there's no effect of permuting the answers because there's no visibility between them.
Right.
But for MMLU, you definitely could permute the answers, yes, although we don't study that particularly.
Thank you.
Yeah, so I guess with this like schematic of sort of idealized potential distributions we could see over correlations in mind, now let's sort of look at real data that we observe. So these curves are this survival or complementary cumulative distribution function that we previously sort of showed idealized examples of, where for each of our metrics in sort of our process of going from loss to accuracy, we look at what the correlation distribution is. And what we see is that for most families, the red pajama family seems to be an outlier for most of these analyses. But for most families, we see a curve that looks just like the green one, where almost every sample is very correlated with compute. So our scores are predictably getting better as we increase compute used for the model. And so for, say, like just the loss or the equivalently the probability among the vocab, the correlations are very strong. But as we shift into comparing against the different incorrect answer choices and see the probability among the choices, our correlations start going to sort of a uniform distribution where as many of them are negative as they are positive. And as we go to a downstream metric like Breyer score or accuracy, we see even more so that there's just sort of a uniform distribution between scores and correlations, or between scores and compute, sorry. And so basically, like as we go further and further away from the loss, we're sort of systematically ruining our correlations that we observe. And there's like a very clean ordering in between the process of transformation that we observe here, sort of these like 3 steps, and how correlation decreases. And so basically like the question might be, why is this happening? And the main mechanism that we think causes this is basically the fact that even though you can predict based on the loss the correct choice's probability, we don't have enough information to predict what the accuracy is without knowing how likely each individual incorrect answer is. So looking at like this graph on the furthest left, this is showing the relation for different samples in the benchmark. The probability among the vocab of the correct choice versus the probability among the choices when we renormalize using incorrects. And so what we see is that if we know what the value of the probability of the vocab of the correct choice is, there's a very, very wide range. It could be almost any value among the choices for its probability. And likewise, if we knew the probability among the choices, we can't easily reverse engineer ourselves back to a single probability among the vocab. And likewise for Breyer score or accuracy, for some locations, there's predictability because if among the choices, our correct choice is more than 50% probable, then we'll get an accuracy of 1 no matter what on that sample, of course, because the other choices can't beat it out. But for other regimes, like it's not super clear whether we can determine that accuracy is 1 all the time, given a certain probability among the choices. And likewise for Breyer score, there's some variability, although it eliminates other variability, but we still can't really go back all the way to the probability among the vocab, because this transformation into the probability among the choices already destroyed our information. And so another natural question to ask might be, okay, now that we know this is the mechanism, is this fixable? Can we use it to predict benchmarks better? And so looking at the actual sort of observed probability masses on the incorrect choices versus the probability mass on the correct choice, there does seem to be some relation where as you make the correct choice more likely, the incorrect choices counterintuitively also become more likely. But there's still a very, very wide range of variability here. So we can't really map one-to-one because this is like a log-log plot, and there's numerous sort of orders of magnitude that our incorrect choice probability mass could take on, even if we knew the correct choice probability mass in the vocab. And so the takeaways of this work are basically that, like, even though previous work has shown that the Breyer score seemed to be better at sort of at not showing this weird emergence and counterintuitive, unpredictable performance, Breyer score still doesn't truly give you anything in many cases, and it doesn't actually make it as easy to predict downstream performance as the pre-training loss. And this is due to basically all of the other information that's not accounted for by the probability mass of the incorrect answer string is fluctuating. And so if you want to sort of evaluate during training a model what the performance on your task is, and you want to sort of get a smooth measure of progress, if your accuracy isn't showing improvements, one thing to try would be testing just the probability among the vocab of the correct choice. And so like this metric might be slightly better than just using loss directly, because at least like a probability among the vocab is slightly more interpretable than just a loss value. But basically the takeaway is that if we want to design predictable evaluations, we're going to have to think carefully about our evaluation setups and our metrics, and decide how to like incorporate these and sort of design benchmarks around what we want them to serve as, whether we want them to serve as like directly measuring sort of downstream performance, or as a useful sort of thing to track it to see if your model is getting better. And so I guess overall for this talk, in conclusion, basically like evaluation is important, but it's very difficult and very sensitive to things you might think not matter, or things that aren't really disclosed in many places. And that these implementation details matter not just for sort of the specific numerical scores, but also the conclusions you can draw or the predictions you can make. And basically, like, I think scaling predictable evaluations are very important to study, but definitely need more work to sort of codify them very thoroughly. But yeah, and if people have any questions, happy to answer them.
Hailey, maybe one quick question could be, so perplexity type of scores, they're intrinsic metrics. They're directly related to the objective function itself. So if we were to consider some of the extrinsic metrics, like glue or Flask framework, do you believe that they would definitely always be better for downstream evaluations, basically? Or do you believe they might be better for being scalable, at least, since they're not as intrinsic to the training objective in itself? I don't know if you have any thoughts on that.
Yeah, I guess so. There has been some work trying to predict sort of scaling laws for metrics like accuracy or like the blue score. I think that like there's still this like ultimate problem, which is basically like there are sort of a lot of moving pieces in order to predict the score correctly. like in the case of blue score, because you're comparing sort of n-gram overlap to like some arbitrarily chosen like reference answer string, you probably would still run into this issue where if you don't like account for that reference answer string, then that comparison sort of introduces new information that it's not easy to predict. So I think there would still be the necessity to like incorporate more information to predict it cleanly, or as cleanly as the pre-training loss, if that makes sense.
Thank you for sharing your insight. Go ahead, Abraham. I've opened the queue for everyone, so please feel free to ask any questions.
Oh, okay, that's fine. Thank you so much, Hailey, for the presentation. Yeah, so as regards the harness evaluation, so we recently like tried to do some benchmarking for I think Europe's that just passed, and so we first of all started using the whole harness evaluation style where we try to constrain the model's prediction over like maybe say 5 tokens, which is like option A, B, C, and D. So then you have like a probability distribution over them. But what we discovered was that that technique, that way of doing things wasn't really robust to situations where, for example, there is none of the options are correct. So we eventually had that at some point, and it became very difficult to like understand what was going on there. For example, we had models like Gemini models and a couple of other Google models, and maybe some generally some of the models we picked didn't even pick from the options we gave, and it was like so when we try to do like a generative style of selecting options, we started discovering that the models were saying, oh, this is not correct, none of the answers is correct. And the model started giving us some reasons why it's not correct. Another thing we also observed was that we found it more insightful to ask the model to give us an answer, like to pick an answer and also give us your reason for picking an answer. And we discovered that the models that said, oh, none of the options are correct, gave some very insightful reasons why the options are not correct, and that really helped move forward. So I was going to ask about your thought as regards the whole if you think the whole harness evaluation technique is robust, and if you have any way to make it a bit more robust to like be inclusive of these type of problems, or maybe there's something else that you think we can do to solve something like that. Because also, like you said, we also had issues where some of the models will only predict the word, let's say the word there, like I am a boy, which is like the correct option, and the model gives you that and doesn't give you the option. So like those are like my general observations, and I would like your thoughts generally on what you think about this, and maybe some ways to move around it.
Yeah, so I guess like I think the thing about like log likelihood based multiple choice is that it's in some senses like sort of like an artifact of like the original way that we were evaluating models at the time of say like GPT-3. Like I think it's useful when you want to sort of prevent the model from say going off the rails and giving you an answer that's not among those choices. But like if you have a model that's capable enough to generate like convincing outputs, it might be worthwhile to do like a generative task, which I know it sounds like if you're asking the model to produce reasoning, you might have already been like doing. But I think like assuming you care about the model's generation qualities, then like I think generation tasks are definitely more worthwhile if you can do it. But it's just that like log likelihood based tasks, I think especially have a role in evaluating like base models and sort of like the quality of a pre-trained model directly, because they sort of avoid the ability to have parsing failures, and because like they're slightly like easier to get signal from like even a model that can't really generate like long form text, you can still get some signal out of sort of its relative probabilities. So like
Okay.
yeah, so
Finish up. Oh, okay. Thank you so much for that. I think one reason why we also looked at generative style is because we also discovered that more recent models are way better at following instructions compared to like maybe when the harness evaluation came out and given the problem that we had back then. But most of the models that we worked with, they were able to like, okay, first of all, give us like the first token is the particular option we need, and then give some wordings afterwards. So, we were also asking the model to give a rationale for its prediction. So I think if you look in that direction, you see that most models are become capable of handling this type of problem that existed previously.
Yeah, definitely.
Of course. Since we're talking about generation, so I wanted to ask about your opinion on so we're talking about benchmarking and evaluation, and how you think if this is actually a valid problem in the space, and if you think there's a solution for it. So, given the fact that so we keep releasing benchmark data sets in the ML space, and now what you observe is that the models keep beating. So over time, the models keep beating the benchmark, and then people need to go create new benchmark data set, and then after like 2-3 years, it keeps beating. So there's been a theory in the space now that says that the reason why these models are beating the benchmark is because after like 2-3 years of releasing the data sets, there's somehow some form of data leak that's coming from papers that the models have been trained on. It's coming from blog posts and a couple of other things. And one way or the other, the model just kind of learns the discussions from Twitter around, oh, the model's weakness on this particular benchmark data set. And then after 2-3 years of that conversation around that data set, you can now pick like a good corpus from the internet, and then you train it, and then you get to beat the benchmark data set. You get to beat the benchmark data set. So do you think there's a problem that's valid, or what's your thoughts on models beating benchmarks so far?
Yeah, definitely. So yeah, there's definitely like problems with overfitting to sort of the existing benchmarks in the space. So yeah, there's like a lot of ongoing work on data contamination, which is really important work and exciting to see progress. Although we don't really have like a definitive procedure for testing this, especially because there's like many ways to sort of leak information or like sort of overfit to a benchmark without directly training on it, just by sort of picking your data mix to use the one that will give you the best score on the validation set or the test set directly. And so like there definitely needs to be more awareness of this in the field, and more work studying like how to detect overfitting and how to prevent data contamination. I think like some things that the field is moving towards is like test sets that are held privately and not disclosed to people, or at least like two copies of a test set, one that is released publicly and one that's sort of held out so that you can check in a year what models underperform on only the private test set. And also work on like benchmark data sets that are sort of dynamically generated, where like there's some data distribution that you're drawing your benchmark data set from, but maybe you're only picking the examples you use on the fly to make it harder to overfit to specific ones. And so I think like we'll see a lot more of these in the future. And it's definitely an important thing to be aware of. Yeah, I guess in short, like definitely like be wary when sort of models are just steadily getting better on benchmarks. Like make sure the benchmark is first like actually what you care about and not just sort of a proxy for it. And then second, yeah, like make sure you can generalize to sort of unseen data or things that you weren't optimizing for.
Okay, and thank you so much for your thoughts. Yeah, that's good. I think we have some questions on the chat.
Yeah, I think so. About questions having equal probabilities, that does happen like sometimes, just because of like there are only so many like floating point values that you can have the models logit on the given token take on. The best way to handle that is like either to just like decide what you're going to do in the case of a tie, what maybe it's like pick randomly between those two answers. Maybe it's pick the incorrect one. Whatever it is, just like make sure you decide that and like codify it. It shouldn't happen too much as long as you have like high enough floating point precision though. But like, yeah, I would say that like if all of your answers are sort of equal probability, like either, yeah, hope this doesn't happen, or if not, maybe it's better to like generate a chain of thought and then the answer or something. And then, yeah, let's see. And yeah, there is work on showing that like LLMs are not robust to permuting the answer choices, which is another example of like LLMs sort of having failure modes and ways that they can do worse or sort of be sensitive to evaluation setup that are not the same as you might expect from a human, where you could sort of assume in theory that a person who gets the same standardized test question just with like the 4 answer choices in a shuffled order would still choose the same answer. That might not always be the case. Maybe someone who's unsure of the answer will just always guess C or A. But like, it's another example of models not being robust to things that we might expect humans to be robust to. And I guess there are some questions in like the chat about hallucinations, which like hallucinations are very tricky to, I think the thing I'll say about this is hallucinations are very tricky to measure and operationalize because it's always sort of relative to what your source of ground truth is. Like if we had a single source of ground truth and could like automatically say whether a fact is true or not in all contexts, then it would be a lot easier to make LLMs that are always factual. But truth is going to be this thing that's sort of task dependent, or what is a hallucination depends on sort of what's on topic and what's not. So it's difficult to evaluate hallucinations.
I think for hallucinations, if you measure PPL on a token level, there has been a couple of approaches. I think that was a year ago. When the PPL is high, you could essentially assume that the entropy of the sampler actually was too small and it starts to hallucinate. So there are ways to essentially figure out, or at least approximate, if it's a hallucination or not. But there is no definitive, as you said.
Yeah, that's a good point. Yeah, you can definitely try to like estimate the model's uncertainty about some generation, like with perplexity. And yeah, I'd expect that works in many cases, although it's not going to like 100% solve the problem.
Yeah, of course not. There is no 100% in LLMs.
But yeah, 100%.
All right.
Primarily, I just wanted to say thank you. A great talk in terms of like simple perspective of looking at this is that, when you're trying to evaluate a model's ability to come up with a right answer, a chain of thought is counterproductive. The concept of leveraging logics to understand reasoning, I think, is more to the point. So just want to say thank you. Great paper, and I'll definitely dive into it in more detail.
Yeah, thank you very much. I'm glad you liked it.
Yeah.
Cool. I guess if we don't have any more questions, we can wrap it up and probably have Hailey again soonish when she publishes another paper. So
Well, thanks so much for inviting me.
Thanks so much for presenting. Bye.
Yes.
We really appreciate you coming in. Thank you so much.
Thanks for coordinating these things.
Bye, folks.